Hi, this is the Laser Beam Characterizer group for Senior Design Fall 2025 to 2026. We are Group 3. I'm Zachary Andreessen, a photonics engineering student and an electrical engineering student.
I'm Thomas Cunningham, an electrical engineering student.
And I'm Lindsay Smith, a computer engineering student.
And our sponsor is Lockheed Martin. So for this project, the motivation comes from the fact that in many laser labs, it is necessary to know many of the properties of a laser in order to know how it will behave in a system. So for our sponsor, there is a lot of model matching that needs to be done. And so in order to help streamline that process, this system aims to automatically analyze the laser's wavelength, polarization, divergence, and beam quality in order to help with the data collection process that is really important for model matching. So this system will make it so that it is automated and requires very little uh, user input. So for our basic goals for this project, we want to measure the polarization, wavelength, m squared factor, and divergence. Uh, for our more advanced and stretch goals, we want to have a broad range of input powers, broad range of input beam sizes, broad range of wavelengths, and if possible, we also want to measure where the beam is and how big it is. So for measuring polarization, the way that we do this is using the rotating quarter wave method. This involves a quarter wave plate, which we rotate, a fixed linear polarizer, and a power meter. And then we're gonna measure power as a quarter wave plate angle, and this allows us to extract the Stokes parameters as seen in the equation on the right there. So we're gonna have a lens to focus the beam onto the power so that we can have those bigger beam sizes. And we're going to use a stepper motor to control the angle of the wave plate. For measuring wavelength, we are going to use a Michelson interferometer, and this involves a non-polarizing beam splitter, which will split the beam into two arms, which will then recombine into one beam where the path length difference from the two arms creates an interference pattern, which will allow us to measure the wavelength of the beam. We're going to use a lens so that the fringes will be circular. And we're also going to use a stepper to translate the mirror. For measuring the m squared factor of the laser, it is necessary to get a beam profile of the intensity distribution of the beam. And we're going to have to do this at several points along the beam. Now, it's necessary to find the waist, the smallest point, as well as the divergence, or how fast it gets, how big it gets, and how fast it gets far away from the Rayleigh range. And so in order to do this, since many lasers are close to collimated, we're going to focus it down with a lens and then measure the waist and divergence there in order to compute the m squared factor. So we have a 300 millimeter stepper motor stage, which will translate our profiler across the path of the beam in order to get the required profiles to measure the m squared factor. For the divergence measurement, we use a similar system with our m squared factor, but instead of measuring at several points, we measure only at the paraxial focus of the lens. And so we can use the same profiler that we used in the m squared factor measurement and get an intensity distribution at that point. And then from that point, the width of the beam measured at that point, and the known focal length of the lens, we can extract the divergence of the beam. So here's a rough layout of how our system works. We're going to have two irises as shown on the bottom, and this will the user will have to align their laser to these two irises, and all alignment for the system is going to be based on these two irises. It'll immediately go through the polarimeter system so that there are no optics that will affect the polarization before we measure it. And then it's going to go through its focal length lens where it is redirected through mirrors into the power meter. To measure the wavelength, using the Michelson interferometer. So we're going to split off a small portion of the beam using a beam sampler, and this will then allow us to direct the beam to the Michelson interferometer. And then you can see in sort of the center there, you have a motor attached to the edge of your power meter, which is going to be used to scan a fan blade across the path of the beam in order to do a knife edge test. So for our full system layout, we have two layers. On the top layer, we have the Michelson interferometer, which you can see on the left there. And so this is going to be used to measure wavelength, as we said already. And then on the bottom layer, we have our other two systems. You can see on the top of that picture, the two irises, the then polarimeter, then the focusing lens, and then it's redirected to the power meter where a beam scan can be done. Putting them all together, you can see them here, stacked on top of each other. The beam sampler will reflect the beam, and mirrors will be used to direct the beam upward to the second layer. The focal length of our lens is around 800 millimeters. This is wavelength dependent, so we're going to have to measure wavelength first in order to make sure that we have axial focal length, divergence, uh, and so forth. For our polarimeter, we had a custom mount built in order to have an easy system where our quarter wave plate can be rotated with little friction and our measurements can be accurate. So for our full system specifications, uh, we have a wavelength range around 1.2 to 2.1 microns. Uh, Also a maximum power between 1 to 10 watts, minimum power between 1 to 50 milliwatts, and a beam diameter from 4 to 35 millimeters. For our measurement parameters, we want to have the normalized Stokes parameters to be within 5% for all the parameters, wavelength within a nanometer, m-squared factor within 10%, and beam divergence within 10 microradians.
The overall hardware design for the system is fairly simple. At the center, we have an STM32G series microcontroller housed on its own PCB board. The power for the whole system comes from a 12-volt DC wall adapter, which is broken out into 5 volts and 3.3 volts. The 5 volts powers the photodiode TIAs, while the 3.3 volts powers the controller. The 12-volt power also goes directly into one of the TIAs and all three of the stepper drivers. There is also 5 volts going to a DC motor controller for our profiling stage, and all of the data that is collected and processed from the photodiodes is communicated through USB back to a PC for processing and presentation. We're using three stepper motors in this project. One of them is for rotating the quarter wave plate, and two of them are for translation stages via ball screw systems. The translation stages come pre-assembled standard CNC stations. The stepper motors are have superior accuracy with angles, which is very important for these high precision optical measurements. For the profiling, we needed to ensure that we had a constant speed, which DC motors were the best option, and with an encoder provide very accurate and stable speed control.
So for some of our optics hardware selection, there's a few parts that were really important to consider to make sure that we meet all of our specs. So for the power meter head that we selected, we picked the S148C power meter head from Thor Labs. There are many advantages to this, but the two main ones are that it has a relatively large input diameter, uh, which is much of about 5 millimeters. And this is much better than many photodiodes, which only have an active area of around, 1 millimeter squared. So we can fit a much larger beam on this detector, uh, as we do our profile and scan across the path of the beam for the m squared factor and for divergence. Additionally, it also has a much lower responsivity than many photodiodes within the range of around milliamps per watt instead of amps per watt. And so this means that we can achieve those really high powers we want to obtain without having to do a ton of attenuation. For the beam splitter for the Michelson interferometer, we chose this beam splitter from Thor Labs, UFB S0502. And this one has many advantages. For starters, it spans our whole wavelength range, which is really useful. And it has a very good 50-50 split, as you can see in the graph on the right there. It's a very even 50-50 split across the entire wavelength range. Now, on the downside, plate beam splitters can have many ghost rays, which will make it a little bit difficult to align. Additionally, this is optimized for P polarization, but because we're going through a linear polarizer in our system, we should already be in that polarization state. So that will not be an issue for us.
For the MCU selection, we chose the STM32 over the ESP32, mainly for its better ADC, which is more accurate and linear. So it provides a higher ADC rate and with lower noise, which is critical for our system since we don't need a lot of noise with our precise measurements. And then also another advantage of our STM is its native motor driving software, which is important since we also have multiple motors for this project. And another advantage would be that it's a more standard microcontroller that's used in industry and overall more robust than the ESP32.
The main board, as mentioned before, is centered around the MCU with a lot of motor driver circuitry. And the blue square on the bottom is the basic circuitry for the MCU. And on the top, you see the full stepper layout with optocoupler circuits on the bottom and pin breakouts on the top so that we can easily click the drivers right into the board. Um, on the right in cyan, you see DC motors. The middle and the magenta are our TIA breakout pins, and the green are where our regulator boards will go. We decided to go modular for regulators in case we ended up having issues with them. Here's a picture of our board all put together. You see on the top are all three stepper motor drivers. On the right side are the two regulators with an assorted number of breakout pins for our different functions. The motor driver utilizes a DRV8825, and the schematic was taken right out of the data sheet. The layout also closely followed the data sheet with a couple modifications just due to space constraint. And the pins are designed to be replaceable with standard drivers you can buy online to make testing a lot faster.
So we have two photodiodes with TIAs in our system. The first is going to be used in the Michelson interferometer. So we have a simple extended in-gas photodiode, which has an 800 to 2600 nanometer spectral range. And so we use a TIA with a 2 kilo ohm resistor in the feedback loop, and an OPA 129 op amp is used for its low noise features in order to convert the light signal into a voltage signal that we can read with our microcontroller. For the other photodiode, this is embedded in the power meter head that we selected from Thor Labs. Now, in order to make sure that we can read a broad range of power, we scan across the beam, for instance, we need the gain of this TIA to be variable. So we used an ADG 1211 voltage controlled switch, which will allow the MCU to control the feedback resistance of the TIA. These are wired in parallel. You have four resistors wired in parallel. And so whichever switch is open will determine which resistor is selected in the feedback loop. The resistors are selected so that every gain state has 10x more gain than the previous gain state. So this will allow us to reach a really broad range of input powers and assist in making sure that we can get accurate measurements across a broad power range.
For the software selection, we chose to use embedded C as our programming language for the firmware because it allows for our ADC timing to be very precise. We have access to DMA, and then our motor control is able to be driven through the STM directly instead of using any imported libraries. And it gives us a very deterministic behavior. And then for the PC GUI, we chose to use Python as our main programming language because it allows for a scalable GUI for system control and data analysis, and also is able to create some nice looking plots for data visualization. For the embedded firmware software flowchart, we have a simple flowchart of the STM initializing all of its peripherals, like the ADC, DMA, any timers, motors, or any USB. The firmware waits for a measurement plan selection from the GUI, and then when that plan is selected, it configures any scan parameters and any calibration. And then goes through a closed loop measurement process of either motion control, sensor data acquisition, or real-time signal processing. And then any process data is streamed to the GUI for any visualization or additional processing. And then our final beam parameters are computed and the system returns to idle. For the GUI or the software flow chart, it's going to be same kind of simple flow. Once the application is started, it initializes the GUI and loads up any defaults. It should automatically search for a serial communication port to attempt connection to. And then once that succeeds, a main screen is shown and you're able to select the measurement system you want, or it will automatically run all measurement systems in a certain order. And once that measurement system is selected, the GUI will send out commands to start the measurement workflow scripts from the STM32. And then that STM32 data collection is sent back to the GUI for any data processing and visualization.
So some of the problems and troubleshooting we've had so far. In general, one of the biggest issues was just there were a lot of delays with our sponsor in getting hardware. So we didn't get most of our major parts until around the second week of March. So we've been really rushed towards the end of the semester trying to get all this working. In general, also the alignment can be really tricky, especially with large optics and the long focal length lens can make alignment really difficult. So on the electrical side, though, there was a strange nonlinearity that we saw in our first TIA design. This is for the variable TIA, where the resistors were originally wired in series with changing gain states. But there was a weird nonlinearity that made us have to rewire everything, and so now to be in parallel, and that issue was resolved.
The current issue we're facing is only one of our three stepper drivers sockets on the main board is not working and is causing the board to heat up. Um, it's not a problem for testing right now. We can use the other two, but this is something that we are still trying to troubleshoot.
For software, we've been having some problems with the beam profile timing. We have figured out that the data that we want is streaming too late in the timing, and then it's causing delays for our next scan acquisition, which was causing problems with our data collection and the correctness of it. And we figured out that we can do a first scan and that is perfect. So we skip to just repeating that first scan and taking out the repeated scans after that. And then also another problem that we've had was noise filtering with the ADC channel. We've gotten a pretty good fix of it of using a lot of filters, so SG filter, some error function fits, and then we were able to get that pretty much down to a perfect, respectable noise level.
Throughout the whole course of this project, Zach has been the lead. Also, has been in charge of all of the photonics related engineering, including the alignment, the design of the polarimeter Michelson M squared system, and all of the photodiode and TIA design. That leads into the electrical hardware, where I was in charge of the main electrical components such as the main PCB housing our STM, as well as custom motor drivers and the power chain. And Zach took on the TIAs for both of his photodiodes. And on software and firmware, Lindsay handled all of the GUI and implementation of the STM firmware, as well as our main website.